Hey guys, thanks for watching. In this video, we're going to be going over the week 14 concepts for Physics 111. So starting off with sound, we see that the definition of a sound is going to be a mechanical longitudinal wave originating from a vibration of some sort. And we can see that in this image to the right, we have this string here that's vibrating sort of back and forth like this. And as we see, it's causing these differences in pressure in the air around the string. And if we were to graph these pressure changes versus position, like we did here, we see that this actually creates this wave pattern. So this is our longitudinal wave that was originating from a vibrating spring. So basically, this here is our sound. So a sound is simply a mechanical longitudinal wave originating from a vibration of some sort. And as we can see, like I mentioned, we have these different areas of differing pressures. And basically, when we have these areas of higher pressure, this is going to be a compression. And then when we have areas of lower pressure, this is going to be a rarefaction. And then we have pitch, which is going to be the perception of a frequency, and hearing will be the perception of a sound. So that brings us into the audible range, and for humans, that's going to be 20 hertz to 20,000 hertz. So anytime we have something below 20 hertz, it's going to be called infrasonic, and anything above 20,000 hertz is going to be ultrasonic. This is going to bring us into the speed of sound, and most of the time we're going to be dealing with sound in air. So for air, the speed of sound is going to be 331 meters per second at 0 degrees Celsius. And this is actually going to increase by 0.6 meters per second for every degree Celsius that we increase. And that's why we have this equation here where we can plug in our temperature in Kelvin, and then that'll give us our velocity in air at basically any temperature. And then when we're dealing with other materials, we would take the elastic property of the material divided by the inertial property of the material and take the square root of that, and that would give us the velocity of the speed of sound in these other materials. We're not really going to be using this equation very often, but I do have a table here on the right that has a couple different common mediums that we would maybe want to find the speed of sound in. So it's a good idea to take a look at that. Alright, next we're going to be covering sound intensity, which is actually the measure of the energy within the wave. And this is always going to be proportional to the square of the amplitude. So we have the equation here in order to find sound intensity, and we can see that this is going to be power over area. And in this equation we're dealing with a point source. And we can see that the area is actually the equation we would use to find the surface area of a sphere. And basically the reason for that is if we had a point source of some sound, that sound would technically move in all directions equally, forming sort of this sphere around the source, and that's why we want to be using this 4 pi r squared here. And this brings us into two different sound intensities that are important to know. This is going to be the threshold of hearing, so basically the lowest sound intensity that we can actually perceive and hear. This is going to be I naught, which is 10 to the negative 12 watts per meter squared. And then the threshold of pain, which is basically where a sound has a high enough intensity to cause pain, is going to be I, which is 1 watt per meter squared. So this brings us into the different sound intensity levels. And this is talking about loudness. So this is another human perception. Our hearing is actually logarithmic, and in order to approximate these sort of loudnesses, we're going to use the decibel level. And in order to find the decibel level, we would want to use this equation here. And then for I naught, once again, we're going to be using our threshold of hearing. And then I have a couple different examples over here in this table of different sound intensity levels. So in this column we're dealing with decibels, and then here we're dealing with our normal intensity, which we talked about up here. And as we can see, at about 10 decibels, we're actually going to have a sound that's about as loud as the rustle of leaves. For instance, if we had 60 decibels, it'd be like a normal conversation. And then at 160 decibels, this is actually a sound level so high that we would burst our eardrums if we were to hear this. This brings us into the Doppler effect, and this is a change in pitch due to the motion of the source and or the observer. So basically, either the source is moving, the observer is moving, or both of them are moving. And when they're moving towards each other, this is going to create a higher pitch, and then when we're moving away from each other, it's going to create a lower pitch. And we can see that in this image over here. Basically, we have a car that's moving in this direction, and it's making some sort of sound, so whether that's an engine or a horn or whatever, it's moving towards this woman at location Y and away from this man at location X. And we can see, if we were to draw a line sort of from where the sound is originating, we can see that to the left or towards the side of X, we have greater distances in between these sound waves, whereas towards the Y side, we have really small distances between. And basically, that's due to this car's motion as the sound is occurring. And over here on this side, the woman would perceive a higher pitch, whereas the man would perceive a lower pitch because the car is moving away from him. This brings us into sonic boom, which is actually a shock wave caused by the constructive interference related to an object moving faster than the speed of sound. So basically in this image over here, we have an object that's moving faster than the speed of sound, and we can see that because our object is this little green arrow here. It's actually ahead of the sound waves that it's creating. And when this happens, our sound waves sort of line up here on the edges and create these areas of constructive interference. And this constructive interference is actually going to cause a physical shock wave to occur. And we can see examples of this with certain airplanes which can fly faster than the speed of sound, which is why that's actually not allowed over neighborhoods in such areas, because this shockwave is actually strong enough to break windows and things like that. So this is caused by the constructive interference that occurs when the object is moving faster than the speed of sound. Alright, next we're going to be talking about beats, which is the interference of two waves of a slightly different frequency. This is going to cause an alternation between constructive and destructive interferences. And we can find the beat frequency by taking the difference of the two frequencies which are involved. We can see an example of this on the image on the right. We see we have wave 1 here, which is going to have a certain frequency, and then wave 2 is going to have a slightly different frequency. And basically when these guys interfere, we're going to look at the resultant. And the resultant is going to show that we have areas of this constructive interference, and then alternating between these constructive interference, we have destructive interference. And basically this pattern which forms is going to be giving us these sort of beats, which is just different sound intensity levels caused by the constructive and destructive interference that's alternating. This brings us into resonance, and in order to better define resonance, we're going to start off with the definition of a force vibration, which is when an object in contact with a vibrating object is forced to vibrate. So basically we have an object that isn't vibrating, but it's near another object that is vibrating, and that's causing the first object to vibrate. And then when the frequency of a forced vibration on an object matches the object's natural frequency, an increase in amplitude occurs. So basically our amplitude is going to increase when our natural frequency is the frequency at which the object is vibrating. And this increase in amplitude is called resonance. This is going to bring us back into a little review on standing waves on strings. We have to remember that when we have a fixed end, this is going to create a node, and then a free end will create an antinode. And then a string fixed at both ends is going to have the following natural frequency. So this is a review from last week, and this brings us into standing sound waves in tubes. So this is going to be for mainly wind instruments. When we have an open end, this is going to create an antinode, so like a free end on a string. And when we have a closed end, it'll create a node, so like a fixed end on a string. And then our lowest frequency that gives us a standing wave is going to be known as our first harmonic, and then higher frequencies after that first harmonic will be our higher harmonics. And then when we have a tube that's open on both ends, this is going to be similar to a string fixed at both ends. And we see that this is actually going to be the same equation we use for the string, where we use n, 1, 2, 3, and so forth. And then a string or a tube that's open on one end and closed on the other end is going to be similar to a string fixed at only one end. And then we have this same equation we would use for a string fixed at one end. And for m, we're going to want to use values such as 1, 3, 5, and so forth. Alright guys, this is going to wrap it up for this video. Thanks for watching and good luck on your finals.